So our next speaker is Mitchell Wagner. That's going to be speaking on glucose restriction during normothermic ex-situ heart perfusion eliminates edema formation. So Mitchell is a first-year medical student at the University of Alberta. He's got an honors degree in immunology and infection and a certificate in biomedical research. He completed a master's in experimental surgery in heart perfusion optimization, and his research interests include ex-situ heart perfusion with experience in radiology, respiratory medicine, and cardiology. Mitchell.
Thank you very much for the introduction. All right, let's see if the big button works. All right, so yeah, thanks for that introduction. I guess I'll jump right in. So in 2022, the Heart and Stroke Foundation of Canada reported that, the Heart and Stroke Foundation of Canada reported that heart failure in Canada was complex, incurable, and on the rise. And they reported that 750,000 Canadians are currently living with heart failure as of 2022. We get 100,000 new diagnoses each year in Canada, and around $2.8 billion per year is spent on care for heart failure. So, and these numbers are only set to get worse as we go forward. And so there's going to be more individuals reaching end-stage heart failure and therefore a greater need for heart transplantation. And so here I'm showing you a graph of the heart transplantation volume since globally since 2000. We've been able to double our heart transplantation volume from around 400 or 4,500 to 10,000 in 2023. However, you can still see that in Canada, we still have wait lists and we still have individuals who are dying on the wait list. And therefore, we need to find ways to get even more organ supply since there's such a great demand for these organs and these procedures. So one way that we can do that is using this new technology called Ex-Situ heart perfusion. So the standard rate now for if you procure a heart is that you put it on ice and you transport it to the recipient, right? And this only affords us around 4 to 6 hours of out-of-body preservation time. However, if we use Ex-Situ heart perfusion, it can lengthen this out-of-body preservation time by using a machine to continuously perfuse that heart while it's apart from the body with sort of like it's called a perfusion solution. We call it perfusate, which is a mixture of blood and a buffer solution. And so you're able to deliver oxygen, electrolytes, and metabolic substrates to the heart while it's apart from the body, which is it's very fascinating stuff. And it also maintains the heart at temperature. So when I say normothermic, I mean body temperature, but ex-situ heart perfusion can be conducted at even hypothermic temperatures as well. And right now we know that ex-situ heart perfusion appears to be an improvement to ice, but it still requires optimization in a lot of areas. And we know that it needs optimization because even though we're able to get longer preservation times up to, there's some reports of 11 hours of out-of-body time as compared to 6 maximum for static cold storage, we still know that cardiac function declines during ex-situ heart perfusion. And this is concerning for post-transplant viability and, prevents us from transporting these organs even further. You can see on the left, don't worry about the two groups there, but basically this is just showing the cardiac index, which is the cardiac output on the machine, over perfusion. You can see that it drops quite precipitously. So our lab is interested in figuring out why this functional decline occurs. So if we can mitigate it, then we can preserve these organs for even longer and do more transplants. So previous studies by our group show that alongside decline, glucose catabolism is downregulated in favor of glucose being shuttled into non-oxidative pathways, so pathways that don't contribute to energy production. And we get a lot of oxidative stress developing in these hearts. The main strategy for when you have a heart on this device is you give it a lot of glucose and insulin. It's aimed at postprandial or post-meal levels. And we hypothesize that this may be contributing to some metabolic dysregulation because if you think about it, in a diabetic individual, they have very high levels of glucose and insulin. And we know that these individuals experience diabetic cardiomyopathy acutely and chronically. So our hypothesis was that perhaps a fasting glucose approach or using an alternative substrate could improve preservation during ex-situ heart perfusion. And so you're probably wondering, what is that alternate substrate? So we're actually interested in using ketones for ex-situ heart perfusion. As I show in the bottom left here, pyruvate kinase is one of the kind of end enzymes for glycolysis, which processes glucose, obviously, to get metabolized. And we know that its activity is decreased during ex-situ heart perfusion. So presumably there's kind of a blockade in glycolysis in producing this pyruvate. However, ketones are produced by your liver actually during starvation conditions. And the unique thing about ketones is that they can actually be processed directly into acetyl-CoA, which feeds directly into the Krebs cycle, which we hypothesize may bypass this blockage in pyruvate kinase. And this also avoids some of the potentially pathologic non-oxidative glucose pathways that we know to be upregulated and associated with decline in function on the device. So in order to test this hypothesis, we had 3 different groups. The control is where we kept glucose at postprandial levels of glucose and insulin. And then we compared to a low insulin glucose group where we had extremely low levels of glucose and low insulin provision. And then we also tried giving ketones targeting 2 millimolar. And this is when ketones are thought to contribute to the bulk of metabolism when they're at this concentration or higher. So in terms of our procedure, we actually use a porcine model. We surgically procure hearts from Yorkshire pigs, and we perfuse them on a device which we have developed in-house. And we perfuse them for 8 hours at 38.5 degrees Celsius. So our device, it has pumps which are able to circulate this perfusion solution through an oxygenator. You can see denoted as F there. And then it actually gets put into the vessels as we attach them to some cannulas that are on the apparatus. And so I can't get into too much more detail than that, but just because of time. But we can obtain data from 3 sources. We get myocardial functional performance via the apparatus. We can also monitor that perfusate, so those electrolytes and metabolites like glucose, using arterial blood gas. And we also take perfusate samples throughout the run and samples of the myocardium at the end. Then we're able to analyze those with statistical tests between the groups. So to get on some results, you can see here, these are the main functional parameters. You can see here for cardiac index and stroke work, which are measures of how much work the heart is doing. You can see that in the low insulin glucose group, actually, they dropped considerably more than the control. However, when you supplement with ketones, you're able to bring that functional preservation back up to levels of control. And that wasn't exactly what we were hoping to see. We were hoping to see that it would preserve function even better than the control. However, what's interesting, though, is that when we use this low insulin glucose approach, we actually mitigated a lot of the edema formation. And edema formation is a significant marker of vascular permeability. And if you get a significant amount of edema, you can actually get compression of the microvasculature, which impairs reperfusion after you implant it into the recipient. And we found that actually using a low insulin glucose or even using ketones kind of wiped out this edema formation, which was really encouraging. When we look at the tissue more, we find that these hearts also experience less oxidative stress. So malondialdehyde is a lipid peroxidation marker. And we see that in the low insulin glucose and the ketones groups that had lower oxidative stress, even comparable to a heart that was not perfused, denoted by the INV, the in vivo there. And so one of our hypotheses too behind this functional decline, or this oxidative stress we see in the high insulin glucose levels, is that after you get blockage in glycolysis, that glucose actually goes into alternative pathways. And one of those is the pentose phosphate pathway. This pathway produces NADPH. And while NADPH can be used to make antioxidants, it can also fuel NADPH oxidases, which produce reactive oxygen species. And we looked at the activity of the gateway enzyme, and we found that even in the low insulin glucose and ketones group, it had a high activity, but there was still low oxidative stress in that group. So that kind of ruled out that hypothesis for us. Finally, the thing that's interesting about our apparatus is we're able to directly measure myocardial function while it's on the apparatus, but a lot of clinical apparatuses don't have that ability. And so what people rely on is lactate production. And it's been associated with worse outcomes following transplantation. And it's thought that a high lactate produces a high risk heart. But interestingly enough, our group has kind of raised some issues with this. And this kind of demonstrates that, because in the low insulin glucose and ketones group, we actually had the highest lactate formation of all the groups, yet we still had similar functional preservation. So this kind of shows that there's some problems with using lactate as a marker of transplantation success. All right, so in summary, fasting insulin glucose does not sustain performance, but it reduces the oxidative stress and edema formation, and ketones can preserve that functional performance while improving those tissue characteristics. As I noted, the pentose phosphate pathway seemed to play a little role in edema formation or malondialdehyde formation, but this is still early. And lactate formation during ex-situ perfusion is influenced by substrate delivery, which may make it a poor indicator of prognosis. And finally, some limitations. We only use female pigs for these experiments. We're not able to get access to male pigs. So this may preclude some extrapolation of sex differences. And our model is minimally damaging. These hearts are not subject to any kind of comorbidities or ischemic insult, whereas in the clinic, usually they have a period of cold storage time before they get put on the apparatus and such. So our future directions is to continue to investigate these underlying mechanisms and some signaling pathways regarding nutrient deprivation and the role of those non-oxidative pathways for glucose, and also optimize our ketone dosage, seeing if maybe if we can increase ketone provision, it can give us better preservation. So I want to thank the CDTRP for giving me a chance to present. And I also want to thank the funders as well as the Ray Rajat Surgical Medical Research Institute, which helps us with these porcine experiments and really makes them possible. So thank you for the time, and I'm happy to answer any questions.
A nice talk. I enjoyed that. A couple questions for you. I've forgotten every bit of anaerobic metabolism, alternative glycolysis, but does the utilization of ketones give you higher lactate just from a breakdown product? That's question one. And the second, I may have missed this from a functional perspective. Does edema in the cardiac allograft afterwards matter? Like we certainly see that from a liver transplant perspective, but it doesn't seem to actually have much of a functional significance. Does it matter from a functional cardiac allograft perspective?
Yeah, that's a good question. So I guess in terms of your first question, does ketones actually increase lactate production? Not directly. So those, like I mentioned before, those ketones get broken down into acetyl-CoA, then that gets shuttled directly into the Krebs cycle. But also keep in mind that we gave these hearts glucose at the same time. So presumably if you are providing a substrate which breaks down to acetyl-CoA and glucose also does that, that could also be causing some backup, and then therefore that pyruvate gets used into and made into lactate. And I think that's kind of shows why it's a poor marker of post-transplant function, because it can be influenced by anything you have in the blood at that point, which is not really very well studied at this point in terms of the clinic. And in terms of your question about the direct effect of edema on like the cardiac function, we do know in these hearts that over time on the apparatus, you can see that coronary vascular resistance sort of increases over time. And so that's where we get the idea that it might be blocking off some of the microvasculature, but I don't think it's as relevant in cardiac allografts as it is to other organs. And where we think this might be really useful is actually with lung machine perfusion, because when you get edema formation, that's actually a really big sign of functional loss, and it causes a lot of problems for lungs because of those delicate vessels. So we think that we could maybe translate the strategy over to that as well and see. Yeah, thank you.
Hi, thanks for your talk. My question might be silly, but why are you only able to have female pigs?
That's a good question. I ask this all the time, but you know, in terms of where we get them from, the farm, they take all the male pigs and they use them for breeding purposes. So we actually can't procure them for experiments, unfortunately. And the other thing that, you know, maybe from a more molecular standpoint is in terms of ischemia reperfusion injury, males are more susceptible to ischemia reperfusion injury, which is something that could be mediating some of the stress in our model. But for the sake of our model, we're really just interested in what happens to the heart when it's on the machine as compared to ischemia reperfusion injury. So if we can mitigate, if we can get that out of the picture as much as possible, then that allows us to isolate for any changes that happen specifically with regard to it being on the machine. So it's kind of a weakness when you think about extrapolation of sex differences, but a strength in terms of analyzing the pathophysiology that's at play. Yeah.
Yeah, you might be getting this, but any early data on what could be happening to endothelium, right? ENOS, ICAM, vascular reactivity.
Yeah, so I haven't presented it here, but we actually know that it's been studied quite a lot with varying conclusions, but we haven't really looked at any vascular markers per se in this setting. But it's known that, you know, in the apparatus that there's a lot of it's an oxidative environment, and you get a lot of oxidation of nitric oxide, and that relates to, you know, some vasoconstriction as well over the course of perfusion. But definitely, we know that these hearts as well, they experience some apoptosis, like a small percentage of the cells experience apoptosis. And so we think that, that could also be apoptosis of the endothelium as well, which contributes to edema formation. So perhaps maybe that reduced oxidative stress that these hearts are experiencing here may be leading to less apoptosis of those endothelial cells and upholding that barrier, but we still need to research that a bit more.
Yeah, right. Thanks.
Thank you very much.